In this lesson, we're looking at factoring and we're looking at the shortcuts and special cases. Please remember what you just discovered in doing problem 823 is that you don't have to use a shortcut and you don't have to use a special case. I give the example of driving a race in Mario Kart. If you are running a race in Mario Kart, there are many shortcuts that you can find throughout the game, some of which were designed as part of the game, some of which are just plain cheating because you're using a glitch in the game to get there faster. Either way, if you use a shortcut in Mario Kart, you get there faster and you finish the race quicker. But if you don't see the shortcut or you don't use it, you can still go the regular route and get there all the same. The regular route that I'm referring to is using your 2x2 generic rectangle and your diamond problem. You can always use a 2x2 generic rectangle and diamond problem to factor these shortcuts and special cases. Sometimes you'll have to put a 0 in for the product or a 0 into your generic rectangle or a 0 in for your sum, and it might look different, but still definitely possible, and you can always do it that route. With that being said, what we're going to see is shortcuts and special cases, and if you notice these shortcuts along the way, then you can use them and it will help you to go a little bit quicker. And just like Mario Kart, there's some shortcuts that are really, really challenging to do. And at first, you might lose a lot of races. You might be really, really slow. But eventually, after time and practice, you can nail that shortcut down to the point that you can do it all the time, and it helps you to get there a lot quicker. The same is true with these, because these shortcuts, some of them can seem complex at first. They can be complicated, but the more you practice and the more you try, then the better you're going to get at them and the quicker you'll be at factoring, which is something that's going to be very important coming down the line. Let's take a look at our first shortcut, just x squared. When we have just x squared, all right, that means that the trinomial begins with just x squared. Not a 2x squared, not a 3x squared, not a 4x squared, just x squared. And if it's just x squared, followed by whatever, doesn't matter what follows, that's why it's in white there, then the two groups will be starting with x only. And that's because when you draw a generic rectangle with just x squared, and I'll give an example on this first one here, when I draw the generic rectangle with just x squared, that x squared, using the normal route, would go down bottom left. And that means the only way to get that box of x squared is if the left was x and the bottom was x, because x times x is x squared. So that means that our two groups are definitely going to start with x and x. But what's the next part of it? Well, when we notice that, we see that if we're using the regular route, just using our 2x2 generic rectangle, we see that in this case, 6 would go top right. And if I do what I normally do, which is to take my coefficient of my x squared term and my constant, and I multiply these two together to get my product. Well, in this case, if it's just x squared, that means it's a 1. And 1 times 6 is 6. That means that these two here match all the time when it's just x squared. As before, 5 is always my sum. And I'm looking for two numbers that multiply to get 6 and add to get 5, and that's 3 and 2, so I fill those in. But here's the key. When it's just x squared, once again, this was x. And therefore, if this is 3x, what times x is 3x? Well, this coefficient has to be the number out front. All right, and that's what we're going to see. That coefficient will always match there. So I'm going to end up putting a positive 3 out front. So I know that x times 3 is 3x. Well, likewise, what has to be down here? Well, it has to be a plus 2. These have to match because it was just x squared, because it was just x. Therefore, the numbers from my diamond problem that created my x boxes are the exact same numbers that end up in my group. And that's what the shortcut really is. It's saying I don't need the generic rectangle. I could just use the x from my diamond problem. And therefore, when I go into example 2, I see it's just x squared, so I know my groups are going to start with just x, and I just need the x of my diamond problem, where my constant is the product, and my sum is still the coefficient of x. What multiplies to get 20 but adds to get negative 9? Well, that's going to be a negative and a positive. It's going to be a negative and a negative because it's a positive product. And what multiplies to get 20? Well, 5 and 4. would multiply to get 20 and add to get 9. Therefore, negative 5 and negative 4 add to get negative 9. And these two are indeed my groups, x minus 5, x minus 4. Some of you will shortcut this even more because you'll say, oh, it's just x squared, so I know it's x and x. And you don't even need to do the diamond problem because you're literally just looking here and saying, my product is 27, my sum is negative 12. So what multiplies to get 27 but adds to get negative 12? Well, that's negative 9 and negative 3. And you'll be able to put those answers straight into your groups. So that's what we're looking at as we use the just x squared shortcut. You just need an x in both of the groups, and you just need your diamond problem where our constant is the product because the coefficient of x squared was only 1. And the sum is still the coefficient of x, and you can use that to get to your groups right away. That's our just x squared shortcut. Let's look at our next one. Our next one, perfect square trinomials, is a special case. This is a special case. A perfect square, just as a side note for the moment, I'm just going to put this up here. I'll put it in a different color, orange. I'm going to erase it. But a perfect square number would be examples of 1, 4, 9, 16, 25, 36, 49. Have you figured out the pattern yet? 81, 100, 121, 144, 169, 196, 225, 256, 289, 324, 361, 400. Those are the top 20. I would encourage you to memorize that list. If you want to pause the video and write them down, memorize that list because that list are numbers that we're going to want to look at. How did we get those numbers? Well, that was simply 1 squared, 2 squared, 3 squared, 4 squared, and so on. All right? So perfect square numbers were obtained by squaring a number. In the same way, perfect square trinomials are obtained because we squared a binomial to get it. That's why they're called perfect square trinomials. So let's show you what is this pattern and how do we use it. Well, first off, we see that the pattern shows that the first number there, a squared, is a perfect square number. That means that you can take its square root. The square root of a squared is a, and that we see is part of our group. It's part of the factor. We also see the last term in this is also a perfect square, meaning that you can take its square root. So that means it's going to be there. So you need to search for the numbers that I just talked about. Take a look at example number 1. In example number 1, I'm going to put in blue what you would put in your head. In your head, you look, can I take the square root of x squared? And you'd say, yes, I can, it's x. Can I take the square root of 9? Well, yes, I can, it's 3. And if you can take those square roots, then they make up your group. So x and 3. Now, if this is a perfect square trinomial, then another condition will apply, and you must check for this condition because sometimes it's not there, and then you can't use this route. So this is what makes this route challenging. If this is a perfect square trinomial, not only will you be able to take the square root of the first term and the square root of the second term, but the square roots of those items, a and b, if I multiply them together and multiply them by 2, I will get my middle term. In other words, my x term. All right? So in this case here, I need to double check, and once again, I'm going to put it in blue because this is what you would do in your head. I double check. 3 times x is 3x. And if I double that, 2 times 3x is 6x. Is that what I have here? Yes, it is. It is a positive 6x. Therefore, this is a perfect square trinomial. And then, if it is a perfect square trinomial, take the sign of that x term, that's the sign in the center, and you square the group, and you're done. All right? Now, why is the middle double the product? Let's just take a look at what the generic rectangle would do here for a moment. Well, if I have x plus 3 on one side and x plus 3 on the base, because it's a perfect square trinomial, I get my x squared, which was the squared of the first one. That's a squared. I get my b squared by doing 3 times 3 and getting 9. But look at a times b. 3 times x is 3x, and 3 times x is 3x again. I get two 3x's. That's why the middle x term is double the product of the two. That's why the pattern works out the way it does. Let's use this pattern now to do the second one. All right, so I see here that I can take the square root of x squared. Again, I'll put that in blue. This is what you do in your head. You don't need to write it. I can take the square root of x squared. It's x. I can take the square root of 25. It's 5. So if I can take the square root of those two items, then they make my group, x and 5. Now, I need to test if it works. All right, and this is, again, something I do in my head. Well, 2 times 5 times x. That's double the product of a times b. And that gives me 10x. Is my x term 10x? Well, yes, it is. And therefore, I will take that sign, negative in this case, and I put the sign in the middle, and I've got my groups. Now, these first two, you could have done the just x squared shortcut. But this one also works. However, in number 3 here, you can't do the just x squared shortcut. And so I'm going to check, can I use my special case here? Can you take the square root of 4x squared? Yes, you can. Square root of 4 is 2. Square root of x squared is x. Can you take the square root of 49? Yes, you can. It's 7. Once again, you do that in your head. You don't need to write that down. But if I can do that, then I put the first one here. Square root of 4x squared is 2x. Square root of 49 is 7. And if this is the correct perfect square trinomial, well, then, once again, check in your head. Is 2 times 2x times 7, is that equal to what I get? Well, 2 times 2 is 4, times 7 is indeed 28x. So this works. So I take my sign of positive, that's because it's a positive 28, and I put it in to get my group. One thing that I would like to mention about this route, all right, about this, you must have a positive here. You must have a positive there. All right? You must also have a positive here. Your first and last term in this must be positive for a perfect square trinomial. Perfect square trinomials are positive, all right, in the first and last term because anything times itself is always positive. All right, so be careful of that. Sometimes they'll try to trip you up and throw that at you. If it's not positive, sometimes you can change it with pulling out a -1 as your GCF. You'll talk about that more when we look at factoring completely. Let's look at our next special case. Next special case is a difference of squares. Difference of squares is very similar to a perfect square trinomial, but this time, instead of the two groups being exactly the same, this time, one is positive, one is negative. That's where we get our difference from. And it's also going to have an impact on your x term. Notice there is no x term in there, so there's no middle term. Once again, just like the last time, we do see that we've got a perfect square for your first term in the binomial that's given, which means I can take the square root of a squared, which is a. The last term is also a perfect square term, which means I can take its square root. Square root of b squared is b. That's where I get the term squares from. And I get the term difference because it is a difference of these two squares. So a difference of squares will always be a binomial where they are being subtracted, a difference, and the two values subtracted are perfect square numbers, meaning you can take their square root. So let's test this first one. Again, in blue means what you're testing in your head. Can you take the square root of x squared? Yes, it's x. Can you take the square root of 64? Yes, it's 8. Is it a difference? Yes, it's a difference. Check. All right? And if those characteristics all apply, then you apply a rule. You take the square root of the first one, x, and the square root of the second term, 8, and you form groups with them. Unlike perfect square trinomials where they were the same group, a difference of squares has two different signs. And that's it. Difference of squares is actually easier than perfect square trinomials. Look at the second one. Again, blue. This is what you do in your head. I don't expect it out on your paper. Square root of x squared is x. Square root of 196, if you don't have that memorized, it's 14. And therefore, is it a difference? Yes, it is. And therefore, we write our groups. Square root of x squared was x, square root of 196 was 14, and a difference of squares has two different groups. Done. Look at our last one. I'm just going to talk this one out. Square root of 9x squared is 3x. Square root of 4 is 2. And therefore, a difference of squares is two different signs. Done. All right. Something to know when you're factoring binomials. There's actually two possibilities, and that's it. Difference of squares is one of the two ways that you can factor a binomial. I mean, you can still use the generic rectangle and diamond problem, and you can still use our just x squared shortcut, don't get me wrong. But what I'm saying is, if a binomial is factorable, then it is either a difference of squares or our next shortcut, which is just GCF. Sometimes when you're looking to factor a trinomial or a binomial or anything there, sometimes all you can do is pull out a greatest common factor. All right? And we'll find that this actually is not a shortcut, as I per se. Pulling out the GCF is actually going to become the very first step of factoring completely. And we're going to talk about factoring completely in the next lesson. So pulling out a GCF will become the first step, but sometimes it's the only step, which is what you're going to see here. Pulling out a GCF is really just the reverse of the distributive property. Let's say that I was going to go ahead and try and factor this using a diamond problem and generic rectangle. All right. For this first one here, if I went ahead and I tried to do my diamond problem and generic rectangle, I have 0x squareds and I have 40. So therefore, I'm looking for a product of 40 and the sum of 10. What multiplies to get 40 but adds to get 10? I apologize, I'm jumping the gun there. 0 times 40 is not 40. What multiplies to get 0 and adds to get 10 is what I'm looking for. And that's just 0 and 10. So I could have 0x and I could have 10x. And you get a little confused at this point because you're like, wait, what in the world is going on? In fact, I'm going to switch the order of these just for a moment. You'll see why in just a moment. But you're still going like, what in the world is going on here? Because I can't pull out a factor with 0. 0 doesn't have factors. So therefore, I can't pull out these. I don't even know what they are. But I can pull out a factor between 10x and 40. That's 10. And therefore, if that's 10, then what do the other two have to be? Well, 10 times x would get me to 10x. And 10 times positive 4 would get me to that. And so watch what happens here. I mean, really, I'm just going to do some creative erasing for you to see what's going on. If I just erase this here, all right, and then I move this up, all right, notice that I actually have my original problem right inside here. I have 10x plus 40, all right, and I just merely pulled the 10 out front, and I was left with x plus 4. This would be written as 10 times x plus 4. And that is our final answer there. I can't factor x plus 4 any further. How do I know I can't factor it further? There are no more x squareds. It's not x squared anymore. All right, so if you don't have an x squared, the only option is to pull out a GCF. So what if you do have an x squared, as we see in number 2 here? Well, in number 2, once again, I'm going to pull out a GCF, and if I look at this as just 12x squared and negative 16x, and I pull out that GCF, I see that 4x goes into both of those. 4 is the greatest number that goes into both. And what has to be left? Well, 3x times 4x gets me 12x squared, and negative 4 times 4x gets me negative 16. So I end up with 4x times 3x minus 4. How do I know I can't go any further? Well, once again, there are no x squared, so it's not an x squared inside my group anymore. So I'm done. Let's look at this last one, though. What if I pull out a GCF? In this case here, if I look at this, and you don't always have to draw this generic rectangle. It does help some students to fill in each term into its own generic rectangle piece so that you can pull it out. But if I look here, 3 goes into all those. They don't all have x's, all right? But I do know that x squared times 3 is 3x, and 5x times 3, positive because it matches there. All right, 5x times 3 is positive 15x, and negative 7 times 3 is negative 21. So it gives me 3 times x squared plus 5x minus 7. All right, and how do I know that that can't be factored further? It has an x squared, unlike the other two. In this case, you'd actually have to check, could you go further? And if you use our just x squared, if it did go further, it would be just x and x. However, you'd be asking yourself, what multiplies to get negative 7? With my diamond problem, what multiplies to get negative 7 but adds to get 5? Well, one would have to be negative, one would have to be positive. 7's prime. The only factors of it are 1 and 7. And I can't do a 1 here and a 7 there. That does not get me 5. Therefore, this one is not factorable. All right, so x squared plus 5x minus 7 is a prime trinomial. I can't factor it any further. Therefore, pulling out the GCF was the only thing I could do, and that is my final answer right there. Once again, this is not really a shortcut. It does make some shorter when that's the only thing you can do. It's just a GCF. It's shorter than normal. But this will become the first step that we always do. You always pull a GCF out first. Then factor what remains in the parentheses if possible. We'll look at more of those examples in the next lesson.